Yep, all right. Well, hi, welcome everyone to the first Code.AI reading group. Um, we're going to cover the paper today, evaluating large language models trained in code. This is used in Github Copilot, and it kind of introduces this GPT Codex model. Uh, okay, yeah, so a brief synopsis, what the paper's about. I always like to break down papers this way when I read them. So yeah, like I said, they introduced GPT Codex, or I think they just refer to it as Codex in most of the paper. It's a GPT-3 model trained on Python code, which is used in GitHub Copilot. They quantify the results on this human eval dataset, which is like a custom dataset that they've built just for this paper and just for this task, basically. And they also do some experiments on the apps dataset. It's like a very similar thing. And then, yeah, how does it improve on the prior work? It solves like 28% of these human eval problems, where GPT-J, which is this large GPT-3 style language model trained by the Alpha AI people, gets 11.4%, and the classic GPT-3 model only solves, doesn't solve any, 0%, basically. And so, yeah, why did they actually do this? So you found out that the GPT can already generate code from doc strings, even though it's not explicitly trained to, and there's lots of publicly available code on GitHub. So, hey, if we train a GPT-3 model on code, then it should do code-related tasks such as code generation, which is like the main focus of their work. And how do they pre-train this model? So they take 54 million GitHub repositories. They just look at all the Python code. I think this is supposed to be every single Python repository on GitHub, maybe. Um, and they take this like 180 gigabyte Python files. They apply some filtering criteria to get rid of automatically generated code, and they're left with 160 gigabyte of Python. And this is what they use to train their GPT Codex model. And yeah, the pre-training setup, I think, is pretty much identical to GPT-3. They find that actually they if you don't initialize GPT Codex from scratch, but you fine tune from GPT-3, you get the exact same performance as training from scratch, but it actually converges faster. So that's mainly what they do. They train for 100 billion code tokens. And yeah, they also mentioned that they use the GPT-3 tokenizer, but they have to add these special tokens for white space because there's a lot more white space in code than, I guess, natural language. And I think they say it reduces the amount of tokens by about 30% in total. And then, yeah, these are the pre-training results they get. As you can see, each dot here is like a different size GPT Codex model. And I don't know if anyone's familiar with these scaling laws papers, but find out that basically as the number of parameters increases, you get this nice linear decrease in test loss. So it's a good sign that these models. It's not really saturating or slowing down. So it's a good sign that training these models, larger models on more and more data, you're just going to keep getting this kind of linear improvement. And so they have their nice pre-trained GPT Codex models. And how do they evaluate it? Well, they use this human eval data set. So this is like a novel data set they've introduced for this task. It's 163 handwritten Python coding problems, all with unit tests. I think there's about, on average, 7 or so unit tests per problem. And the solution is only marked correct if it passes every single one of these unit tests. And this is like an example down here. I think they range in complexity. I think this is one of the more basic ones. And then this is all the results they get on this human eval data set. This pass at K thing. So basically, they generate K solutions to each problem, and then it's marked as correct if one of those K generations passes all of the test case for their problem. So you can see, obviously, as you increase K, you're generating more solutions for the problem. This pass rate increases, and they also compare all the different size GPT Codex models against GPT Neo and the GPT-J model, and also Tab9, which I'm not 100% sure how it works, but I think it's a quite popular code generation model. And as you can see, GPT Codex does significantly better than the GPT Neo and GPT-J models. It kind of makes sense, right? It's explicitly trained on Python code, whereas the GPT Neo and J models are trained on the Pile dataset, which has some code in it, but not a significant amount. And Tab9, I'm not even sure what that's trained on. Another observation they make, I guess, is GPT Codex 2.5 build, the second one from bottom, has about the same parameters as GPT Neo 2.7 build, but gets, 4 times the performance, basically. And then some other results. I think one of these things I didn't like about the paper is the results were kind of like all over the place. I'd like them to be kind of collected in one main place, but yeah, GPT-3 on all these problems gets 0%. And they also have this GP Codex S model, which I'll explain in a bit more detail later. But it's basically the GPT Codex model fine-tuned on these competitive programming examples, and that actually beats the best like GPT Codex model. So it turns out, yeah, if you fine-tune this thing on data in the same domain, it does significantly better. So good idea. And again, yeah, scaling laws still important. As you increase these number of parameters, the performance of these models kind of scales almost linearly. And yeah, if you, this mean log p reranking is basically okay. If we generate 100 examples and we look at the one that has I think it's lowest test loss or test perplexity, then that does significantly better than choosing one at random, or I think whatever the metrics. I think they use like a back translation metric as well. And they also find that, yeah, as you increase k, so as you want more generations for your problem, you also want to increase the temperature. So the temperature increases like the diversity of your solutions. And so high diversity is pretty much required when you're generating like lots of solutions, and it's really good for helping you find a solution that passes, basically. Another thing that's interesting is, yeah, so a lot of time in generating code from docstrings work in the past, they use this BLOOM metric. So this is used a lot in machine translation. It's pretty much the n-gram overlap with the reference solution. And they find that basically there's not really any correlation between your BLUE score and if you actually pass the test cases. And I think there's quite a few papers that have looked at this in the past and said how badly BLUE is as a metric for these type of tasks. And yeah, they're kind of just referring it here. So as well as evaluating on this human eval data set, they also evaluate on this apps data set. It's come up quite recently. So yeah, you've got 5,000 trained test examples, 2 different metrics. So number of times you pass all the test cases, which is called strict accuracy, and the number of test cases passed in general, which I think they use because it lowers the variance of the results. And you get 3 input-output examples per example, kind of natural language problem. And this is like an example down here. When applying Codex on apps, they make a few like specific changes. So they only focus on this strict accuracy, so only if your generated code passes every single one of the test cases. And they always append one of these input examples to the doc strings. They kind of call this one-shot learning, similar to like prompts for GPT-3 models. Yeah, and they also do this filtering out thing, which I didn't quite fully understand, but they use these 3 input examples as like proxy test cases, and they only consider, in their kind of filtered results, they only consider examples that pass all 3 of these input-output examples, and if you don't do this kind of filtering, they count it as like raw results. And they also have like a timeout of 3 seconds if your code doesn't finish in time, basically. And then, yeah, we can see the results here. So the apps comes in like 3 different difficulties, I guess. And as you can see, the kind of filtered results have like significantly better performance than the raw results. So it turns out this filtering metric they use is like really, really important for getting good performance. So you can see the one-shot codex filtered pass at 1. It's pretty much the same performance as the one-shot raw pass at 100. And then they do some fine tuning. So this is how they get the Codex S model I mentioned at the start. So they get these 40,000 examples from competitive programming websites, like I think they mention Code Forces maybe, or maybe they don't mention them by name. And they use the Codex model to generate 100 solutions for each of these 40,000 problems. And if none of them pass these test cases from the competitive program websites, and they basically discard this problem, say it's too difficult for GPT Codex to solve, and then they're left with 10,000 filtered examples. And then, as you can see, like I mentioned previously, the codexs model does quite a lot better than the non-S model, let's say. So yeah, turns out if you find so this is results on the human eval data set, I think. And so yeah, so if you pre-train, not pre-train, sorry, if you fine-tune on this data that's quite close to your domain, so it's programming competition challenges, you basically improve results. And then they also, yeah, they do this. I think they, in my opinion, they kind of very quickly went over this and don't think it explained it that well. But they also consider GPT Codex, instead of generating code from doc strings, they generate doc strings from code. And yeah, so obviously there's no kind of test cases for doc strings, so they do each one by hand, and so they only generate 10 per problem instead of 100 like they do for the code problems. And yeah, when they're doing pass at one, they select the top doc string by doing this back translation objective. But the results here I didn't really understand, because this Codex D is the model specifically trained for doc strings, actually does worse than the Codex S model, which is not explicitly trained for generating doc strings. So I'm not really sure why that happened. I mean, maybe someone else has a better idea why. And then, yeah, they spend a lot of time also talking about the limitations of this model. So one important thing is sample efficiency. So obviously humans don't need to look at 160 gigabyte of Python code to learn how to code well. They can learn from a lot less. It still, even though it's trained on all that code, it still generates code that's syntactically incorrect, that won't compile, and uses a lot of kind of undefined and outscope variables. And they find that they have a nice graph in there, which I don't think I included. But basically the performance drops as your doc string gets longer and longer and more complex. And then I have a very brief slides on the hazards, but they spend a lot of time talking about it. Obviously, it's a very important thing. They mention how humans can get over-reliant on the output of the GPT models. So a lot of time it generates code that looks correct but isn't actually correct. They mention this misalignment problem. Obviously, your language models are trained to generate code that looks similar to the training data, and they find that actually a lot of time it kind of sticks to that and actually generates code that is incorrect instead of what your doc string actually wants you to do. They mention bias in the data set. So if you have a data set with toxic language in the comments, your model will probably generate something like that. Obviously, the economic impact of training these super large language models. Insecure code, so this code that has security vulnerabilities. Economic impact is, yeah, it's, GPT Codex is going to steal everyone's jobs and put us all out of work, basically. Environmental impact is the impact on the environment by training these large models. And legal implications, I think they've gotten to a bit of trouble recently, or not really trouble, but people have raised the question of, what type of data is this trained on? Do they care about licensing? And I think they actually mentioned that they don't take licensing into account at all. They kind of just take all code no matter what, which is, people aren't really happy about. And then, yeah, hidden in the appendix, there's this kind of further work section. I feel like they should have expanded this a bit, but their main thing is improving the data that it's trained and fine-tuned on, basically. So they say, okay, if we don't want it to generate buggy or insecure code, then we really should remove that from the data. And we maybe should have some metric of the quality of the data, so we can only generate or only fine-tune on code that's regarded as high quality. And then to increase this like a misalignment problem, where it's not generating the code you want, you should do this kind of reinforcement learning on human feedback. But a lot of this is like very, very quickly glossed over. I think the further work section is quite small. And so, yeah, so that's a very high-level view of Codex, a super large language model designed to produce functionally correct code from a given doc string. Performance is on par, solving the easy interview questions, let's say. And yeah, it turns out if you fine-tune these models on competitive program examples and produce multiple solutions instead of just one, you get significantly better results. And then some extra things to mention, obviously, GitHub Copilot, which is this VSCode extension, makes significant use of GPT Codex. There was a really nice article by Jeremy Howard from FastAI. He kind of says, is GPT Copilot actually a good thing or a bad thing? I just found this recently. I think someone tweeted it. There's someone else's discussion about the GPT Codex model from Henry AI Labs. He usually makes quite good videos, so maybe he explains some things better than I do. And yeah, there's been quite a few discussions of this on Hacker News. So if you just search GitHub Copilot on this Hacker News Algolia thing, which searches Hacker News pretty well, you'll get all the discussions there. And yeah, obviously, finally, that's why we're all here. So from the Hugging Face Flax Community Week, we created this community and we trained this GPT Code Clippy model. It's open source. It's available at this repository, and we also have, made by Nathan, this pretty good VSCode extension. So if you want to use GPT Code Clippy, or I think it works with pretty much every model that you can use in the Hugging Face Inference API, you can use it to generate code in VSCode. And yeah, that's it. That's a super high level explanation. And that's GPT Codex.
Thanks, Ben. That was really
And
good.
yeah, I guess, yeah. Does anyone have any questions?
Awesome.
That was really good. Thanks, Ben.
Cheers.
Good one, Ben.
All right. So, now it's like the time for us to discuss. So one of the things that we've had, I guess, Nate, we can talk a little bit about pre-training from our own experience. One thing that stood out to me is that they focused on one language, and their data set is pretty big compared to the pile for Python only. Any thoughts about that?
So specifically, I know that the pile only has about 5, I believe, gigabytes of Python code. So it is very interesting that it's still able to perform so well, like the GPTJ model, with having such little training data on Python. I wonder if having the multiple languages, contributes to improving the Python specific task.
Or is it because they did, kind of filtering, they did some specific filterings, right? Like, instead of taking that entire thing, they had, popular repositories and stuff.
Yeah, that too. The filtering probably plays a big role. I'm surprised that they didn't test out with their future work ideas of removing buggy and insecure code.
So, with respect, I think someone made this point, right? So, having multiple languages might have helped it. If it was in the case of JavaScript or C#, right? So, two languages which share a lot of syntactic keywords together, I guess it would have helped over there. But for Python, I couldn't, quickly think of some language which has very close syntactic resemblance to it. So
Maybe English.
You guys should check out COBOL. It's like, writing English. It's not even like coding.
Oh, really? Okay.
Yeah.
Yeah, I wonder if this supports a theory of there is a universal language that's shared amongst all other languages. So there is knowledge to be gained regardless of the programming language you're pre-training on. Similar to maybe findings of MBERT or MBART when training on multiple different languages at the same time. Maybe to that. Any thoughts?
Rather, I think the natural language prompts might have helped it. So we see a lot of variables with so a read function, a function in Python and in JavaScript, right? Let's say if those two languages are taken into account, so they have a lot of natural language context interjected in terms of variable names, function names, doc strings, I guess it's a big part of doing that entire thing.
They also, I mean, it seems like a lot of just research in this area wants to just treat code as natural language. There are works for using like abstract syntax trees and stuff like that, but they haven't worked well, sadly. And it seems like a waste because one of the things that you should be able to do is abstract away like the actual syntax of these codes and just represent multiple programming languages as like abstract syntax trees.
Universal abstract syntax trees, yeah.
Yeah, universal ones, yeah. Instead of having to care about what language or even having to train like a MBERT or a MGPT for these. But none of the approaches so far have seemed to work. I don't know if it's a scale thing or if it's or what.
Yeah, I wonder. It's very interesting how programming languages, even though like as Ranjith pointed out, there is the common element of NL or inline comments and header comments. But when we add in more programming languages, the syntax is very different, and it's not super comparable to like human languages in terms of like when training on multiple different languages, it's not the same as focusing only on one.
Yeah.
And add to that, can you hear me? Hello?
Yeah, hello.
Yep, can you hear you? Hi.
Hi. So something that bothers me about all of this is that like this work is very interesting and nice, but it rests like on very mainstream languages like Python, Java, and so on. So I'm more interested also in like what happens to more niche languages. And also like I mean these are all like object-oriented languages as well that have been used in these projects. And if you change sort of like the computational paradigm, right, how would it look like, and what we do about low resource languages in general in this space, right? I think one thing that probably should be avoided is that sort of like we enter in some sort of like echo chamber of like programming languages where new languages don't have a chance because these solutions only work for already well-established languages, right?
Yeah, and it would be very sad because if we go the same way as like natural languages where it's really difficult to find the training data and also the models are just super inefficient on trying to learn a new language, because for humans, I mean, it's relatively easy to switch from one language to another once you have one of them sort of down pat. Way easier than trying to learn another natural language, like going from English to Spanish. And so it seems like it should be way easier. But if we use these sort of language model approaches that we're doing right now, seems like I don't feel like we would probably get there.
Or something like what Nate said some time back, a universal abstract syntax tree, and you flatten it out like Code.AI, and then you run a lot of language modeling over it. So now your model generalizes towards everything. I mean, that's one thing, but I think the semantics part would be missed, I guess. So yeah, we won't be able to capture the semantics of each languages. That would be a huge downkill.
Yeah, and also like a lot of programming language, it's not just discussing an idea like with natural language, it's also how efficient you can describe or enact that idea. So one thing that was in the Jeremy Howard blog post was that a lot of the code is just average, like it's not very good code. It's not hyper efficient or anything like that. So yeah.
True. So I don't know if at all that is the case. To train efficient code, they should do a language modeling in 3-state code or something like that. in a very low level language setting, so that every time you generate a good code out of it.
Yeah, yeah.
There was a paper which does that, I think so. Some paper I forgot.
What was y'all's general impression of the Codex paper, like their actual research that they did?
One more thing I forgot is that sorry for interrupting, but they didn't.
No
They
worries.
weirdly didn't talk about code blur, right? They used VSCode to test it out, but code blue is it's like they hit like it's like it didn't exist at all. They didn't use it at all to compare anything.
What is it? Can you quickly describe it?
Code blue. So code blue is separate metric kind of thing which captures semantics and syntax, and just normal blue. It's a paper. I think the work was done by I don't know, people from Microsoft, I think so, or
Okay, I will look it up.
Microsoft, Code blue. So I'll link it up now. This
I
paper.
Yeah, it's from Microsoft.
It's like they didn't even talk about this over here. Yeah.
Yeah. I think they were. Yeah, I can't justify why they didn't. But I think it was still interesting that they tried to look at executability and correctness.
Yeah, true.
It would have been interesting if they did it with code as well, but
I mean, one thing that sort of puzzles me is how, it seems like Microsoft basically just bought this codex from, or at least got the rights to it. But not a single person from Microsoft was a co-author on this paper. And I don't remember seeing, or none of the names here I've found in any sort of software engineering venues or anything. So I wonder if these people were mostly just like machine learning people, not software engineers or new sort of the history
also
and stuff.
Ben was talking about what is that, Tab9, right? So I vaguely remember seeing somewhere that Tab9 also uses linting and other additional capabilities while generating. It's not like normal causal model generating over there. I hope there is something over there, because the CTO of the company is Iran Yahav, I think, from Tel Aviv University, Israel. So I mean, I hope something like that was there. So in some talk, I guess I saw that. I mean,
Yeah, I mean, I feel like there's plenty of tricks in order to squeeze out more points on this evaluation, like test bed that they have. But whether or not it's an approach that we should really be thinking is going to get us to, a real Copilot sort of or a pair programming companion. I don't think this sort of approach is ever going to work, really.
I don't know. You have what was it, Richard Sutton's blog post about the bitter lesson. You shouldn't focus on models specific to code. You should make these super general models because they scale up better. And I think this is like kind of OpenAI's MO basically is we'll just train these super general language models and we'll just scale them massively. And it doesn't care if you have a model with some explicit biases towards writing good code. We're just going to beat it by having a bigger and bigger model. So it looks like this is the approach they went for here.
Yeah, and the issue is that it sort of works almost, but then it doesn't. I like a lot of the examples that he gave, Jeremy, and I've experienced it while using Copilot myself. Like I trust in it too much, where I know that it did not properly write the syntax or something like that, but I'll be like, oh well, maybe it knows a little bit better than me, so I'll go ahead and run the code just to see what happens.
I think so. I've not used it actually with Python. I've used it mostly with Haskell, and Haskell is one of these low resource languages, right? So like it has not many examples in GitHub or in general. And what Copilot ends up being extremely good at is sort of like extrapolating from patterns already established in the current buffer, right? So like if you have some boilerplate code that is repeated above, right, then Copilot figures this out quite quickly. But if you end up with like a more cerebral coding problem, right, where you actually have to think what you're doing there, right, then it utterly breaks down and cannot help you at all. And I'm also using it together with a language server, the Haskell language server, which runs the compiler all the time and sort of immediately shows you what's wrong. So like if I accept a prediction with tab and that prediction doesn't make sense because of syntax error or type errors, I get the highlight immediately, right? So like that gives me additional sort of trust in the system that I otherwise probably wouldn't have. So many suggestions that I can just blindly accept, but I know when I have to accept failure from the system, and which is all the interesting cases, which makes me believe that my job is not in danger here, but like boilerplate sort of goes away.
Yeah, I think that's definitely been my experience as well. It's really good if you're writing like test cases. It's really good at predicting the next test case you're going to write, and you just have to hit tab. But yeah, I haven't really used it for writing a doc string and then pressing tab, and hopefully it writes the full function body for me. But yeah, if it may be good enough at writing, boilerplate is that's all we really need at the moment.
Yeah, that's another thing is I don't know if we really know what we want from a system like this either.
Because yeah, I think this, the code that humans write is at the end of the day meant to be read by other humans, but maybe maybe like a machine learning model can generate super fast code, super efficient, but it's completely unreadable. And I guess there's like a trade-off between maintainability and functional correctness or efficiency, let's say.
Yeah.
To Nate's earlier point about we don't know what we want, I think it would be interesting to actually maybe make a survey or something and study like what do we expect from AI systems that work on code. That might be interesting to learn about. Because researching in this area is like really cool, but I think at the end of the day, we don't want to end up shooting ourselves in the foot. We want to target problems that developers actually have.
Yeah, I worry that this is where AI research for code is headed towards because it's sort of it might be an easier path and what developers actually want and what developers need. And so I'm sure when ever this Twitch stream from OpenAI, well, I'm actually very curious. I won't pass judgment too much, but I'm betting it's going to be a lot of similar stuff like this, where it's just large scaling of pre-trained models, but not a lot of like developer focused experiments and evaluations and stuff like that.
Yeah. We'll see. Yeah. Maybe it's just like another way to show off like capabilities. So like some really cool demo is what I expect. More so marketing for Copilot. That's what I'd expect, but I don't want to pass judgment either.
Ask a question. So like, how much would you pay for Copilot if it was like subscription based?
Oof. As it stands now, I wouldn't pay for it.
Maybe if I was a software engineer and I get paid like 120,000, maybe I'll pay for it.
Okay, so if nobody wants to pay money for it, how much would they have to pay you to use it?
I think they should pay
man.
for data.
Yeah, that would be nice. I wish you know how like there was a they give badges to people on GitHub if like your code was on the Mars rover or if you helped contributed to the code on the Mars rover, or if you contributed to the Arctic Vault. I don't know why they didn't do something like that for this one.
Yeah, that would
Your
make
data
sense.
was trained.
Isn't there somewhere they mentioned how they used every single piece of data on GitHub, or did I make that up? I think it's in the Copilot press release thing.
I think they said just a massive amount of public repositories, but it is very bottom. I think they discuss it. Let's see.
It also stood out to me that didn't filter by repositories, they filtered by files. So they're assuming that they're interested in very long programs, essentially, not so much the source of the program, the repository.
Yeah, there's no like metric for quality or um how yeah, well basically yeah, quality is the main metric I guess. But obviously if you do that you're gonna get significantly less data and maybe it's not enough data for training these type of models.
Yeah.
Yeah, what they say specifically is that it was trained on a selection of English language and source code from publicly available sources, including code in public repositories on GitHub. But they don't say that it was all of it. They don't even say that it was only GitHub, so they might have gotten stuff from like Stack Overflow and stuff like that, or like Bitbucket or GitLab. My biggest gripe with their evaluation is that they didn't talk about how they chose the problems. Like they handcrafted them, but they don't give any criteria for how they generated them. Was it generated from authors? Did they use some sort of template scheme? Um, and they also like they don't break it down on the types of questions. So one thing that I think would have been interesting would be having a taxonomy of the types of problems that they asked, whether or not they were like math related, string manipulation type problems, those types of categories. And that way we could sort of see where this model's failing. Is it unable to do string manipulation? Can it not do mathematical operations very well? The raw number that they give you for the pass rate and stuff, I don't really think tells us that much, especially since it's so low.
Yeah.
Yeah, 'cause I think the only thing they really mention about it is they had to handwrite all these problems because they didn't want to use problems that might have been in the training data. But yeah, there isn't any kind of breakdown, let's say. Also, did anyone read or understand properly the like pass at k? They use this like n choose k type formula to like reduce the variance. I kind of skimmed over that, but I didn't fully understand why it was done. Maybe someone can explain that to me.
Could you repeat that?
So on page, the bottom of page 3, they mention how they calculate this pass at k thing, and it uses this like expectance over 1 minus n minus k choose k over n over n choose k, and they say it's like less, what is it? Less biased estimation, but I didn't fully understand that. I was just wondering if anyone else did, or maybe it's just me.
Yeah, no, I didn't for sure understand.
I think yeah, looking through the paper as well for Microsoft related authors, like someone mentioned, I think there's literally just a mention of thank you for GitHub for partnering to build GitHub Copilot, and thank you to Microsoft Azure for supporting model training. And that's it, basically.
Yeah. So I don't know how many people out here are like actual software engineers.
Because yeah, I mean, Microsoft does, yeah, I think like someone said before, they do have like a lot of work or research on machine learning for code. But yeah, you would have thought at least somebody would have been in the paper. I mean, yeah, maybe GitHub was, or OpenAI was just like, okay, we'll do this, and then maybe there'll be another paper in a year's time, GPT Codex 2, and it has all the Microsoft authors in it as well. It'll be significantly better.
Yeah. Yeah, that's my hope because right now, yeah, I didn't particularly like the paper. Um, it's cool, the demo and stuff that came out of it, but the actual research and the way they presented the results and stuff was it was very copy paste of like just machine learning papers where they define a very specific benchmark. They have no sort of human subject participant evaluation on how useful it actually is. Um, no
Yeah, okay,
statistical
that's a good
rigor.
point. Yeah, there's no actual like human benchmark. Also, I guess, did anyone else look at this docstring generation section? Because again, I still don't understand why this GPT, this Codex D, which is specifically trained on docstring generation, was worse than Codex S, which isn't trained for docstring generation. I don't know why that would be the case. And they don't really explain why.
Oh yeah, this one I sort of just ignored, to be honest, because they don't even say how they rated the docstrings. They don't say who did the rating. Like, was it multiple authors? Did the authors have some sort of like debate, like open code debate on whether or not a doctrine passed or not? They have like no discussion on it.
I think they mentioned, I don't know if it's in the appendix or not, but yeah, they just generate these like 10 docstrings and I assume it's someone from OpenAI looks and says if it's good enough, so it then counts as correct. But yeah, again, I guess it's difficulty of like uh, how do you evaluate like generated text basically, and it's kind of a very difficult problem.
Yeah, I mean, at least what I would have at least expected would be here's some criteria. So did the doc string have all the parameters correct or something like that? If this is like like a Java doc type of thing, um, did it say what was supposed to be returned? That sort of stuff. That they would have some sort of criteria. They would mention that they tested on.
Yeah, in the paper they say, where is it?
Page number 9, I guess, 9 section.
Okay, yeah, so. Da, 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 da. Where is it? So I did. I swear there was a section where they specifically talk more about it. No, I can't find it.
Yeah, I guess.
Section 5. Or you mean like they go into more detail?
Yeah, I swear there is like a few sentences where they say, "Oh, if a docstring says X, Y, and Z, then we ignore it." Or okay, yeah. So the docstring generation, the most common failure modes we observe when the docstring model leaves out an important detail, such as answer must be to two decimal places, or when it over-conditions on the function name and invents a problem unrelated to the function body. And then
Oh
they say also,
yeah.
Yeah, it's
we
happening.
grade sample doc strings by hand, considering a doc string correct if it uniquely and accurately specifies the code body. But again, yeah, that's quite vague.
Yeah. Also, when they say common failure modes, they don't give any numbers. Like how often did it fail? Um, like where are any of the statistics on any of the results? It's so strange.
Yeah, I feel like it was kind of an afterthought, and they kind of shoved it in there. But if it's not
Yeah.
really kind of explained upon, then maybe you shouldn't really put it in there, I guess.
I mean, it's fine to put. I don't want to, if I was a, reviewer, I don't think it would, kill the paper. It's just that it's just odd that they just don't add, that it was like, 1 out of 5 or whatever, that it was missing this details or something like that. Um, I would definitely ask them to add that in because it's very useful. Because reading the section, I don't really know what to make of how good the doc string generation is.
Is there some examples in the appendix, or no?
I actually didn't go through the appendix, so good point.
It's another one of those papers where the appendix is longer than the paper itself.
How dare they not use uh, syntax highlighting in their appendix?
Yeah, Appendix D covers example code generated. But I don't think there's actually a bit on showing the example of the doc strings generated. No, I don't think there is. So it's literally just that one very small section in the main paper. But I mean, yeah, I guess the whole point is to generate code from doc strings. Yeah, it doesn't really matter if it does a poor job at generating doc strings. I actually think that table with GPT Codex S and D, I think maybe this is like mislabeled because on the kind of caption for the table, it's like we find similar but lower pass rates. Oh no, lower pass rates compared to Codex X. So yeah, so they admit that it gets lower pass rates than Codex S, even though it's explicitly trained for generating doc strings. But they don't kind of question why. Yeah, anyway, it's just a weird section. I don't know. Did anyone have any thoughts on the broader impacts and hazards and anything like that? I think they did a quite a good job at covering quite a lot of stuff.
Yeah, me too. The only one that was, I think, not well done was the legal one. Because I guess they really just went uh, to say that it's fair use, and so they sort of food everything else away.
Yeah, so I think the last paragraph in that section begins with our commitment to responsible and safe AI includes continued attention to the broader intellectual property implications. But they didn't really care about that when training the model.
Yeah, I feel like they probably. Well, I don't actually know how it came about.
Yeah,
Um,
I don't really know the legality of all this stuff, but they like to say everything's fair use. So maybe it is. I don't know.
yeah, not sure. Not sure.
But yeah, I would have liked to have seen it on this Code SearchNet dataset and this Codex Glue dataset. I would have liked to have seen how well it actually does on that compared to, I think, previous works are like CodeBert. I think there's a CodeBert paper, but they again they don't really compare against stuff like that.
That was another thing that was a bit shocking to me, and why like I don't think a lot of them might be like do software engineering research, because CodeBird, GraphBird, Codex, Glue, those are all Microsoft research, and so you'd think that they would at least evaluate it on that type of stuff, because there are problems in the Codex Glue benchmark that deal with code generation and stuff like that. Um, so it's shocking to me.
Yeah, but I guess it's another one of these papers where it's like, okay, we'll make our own data set and we will, it'll be heavily biased towards what we're trying to do, and we'll say how bad everyone else is. Well, okay, they only really compared against GPT Neo, GPT-J, and Tab 9, and everything else they kind of pretended it didn't exist, I guess.
Yeah, I think they do mention CodeBird in like which is Python T5 or PyM T5, which is a T5 model trained on Python data. So it seems like, yeah, they even mentioned CodeBird. So I mean, it seems like they at least knew about it. They also knew about the people behind Code Search. So yeah, weird. All right, so I say let's go ahead and wrap up our session today. Thank you, everyone, especially Ben, for making this awesome reading group session. We are hoping to be able to do this regularly. So one thing that will be important is during this weekend, we'll try and organize what's going to be the next one. So if you're interested, make sure to vote for whatever paper that you would like to be see next time. And we'll also be finalizing the time that we're going to be doing each week to try and keep things consistent. So we'll also have something where you can vote on the time. But yeah, thank you everyone for coming. I hope you all had a good time.
Yeah, thank you all. This was really
Cool. Yeah, thanks guys. Thanks for coming and thanks for listening.
Thank you.
Thank you.
Thank you all. Take care. Bye.
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 Bye.